Howdy. Today's video is on acid-base theories. Acid-base theories provide a framework for understanding a lot of different reactions, a lot of different compounds. The theories are conceptual tools that will help you understand how some compounds react and why some reactions have larger Eckhart constants than others. What you should be able to do after watching this video is be able to distinguish between the three acid-base theories talked about and identify when they can be applied. Identify the difference between a strong acid and a weak acid, between a strong base and a weak base, recognize strong acids and strong bases, recognize polyatomic ions and their behavior, relate acid-base chemistry to equilibrium concepts. Now there's over 10 million compounds. There's nearly infinite number of compounds. In the last NIH database, I think there was over 10 million distinct compounds with distinct chemical and physical properties. Now, we don't want to think about that many compounds, and so we have to develop theories and models so we can categorize them and make it a little bit easier. And some ways of categorizing different compounds are the ability to donate or accept protons. A proton is just a hydrogen ion, and that's the basis for Bronsted-Lowry theories of acids and bases. Another way of categorizing a compound is its ability to donate or accept a pair of electrons, and that's what Lewis theory acid-base is based on. And so the three acid-base theories that we'll talk about, now there's actually more than just three, but typically we'll talk about these three. They're the three main ones, the most common ones. There's Arrhenius theory, Bronsted-Lowry theory, and Lewis theory. Now Arrhenius theory was the first developed. It's the simplest. The basic concept behind Arrhenius theory is if you add it to water, if it produces hydrogens, it's an acid. If you add it to water, if it produces hydroxide ions, then it must be a base. Now you can only use Arrhenius theory for aqueous solutions. And again, you're not talking about reaction, you're just talking about when you add it to water, what happens. Now Bronsted-Lowry theory and Lewis theories are a little bit more complex. They look about how a compound is behaving in a reaction. And so for both Bronsted-Lowry theory and Lewis theories, you could have something behaving like an acid in one reaction and it behaves like a base in another reaction. It depends on what it is reacting with. Lewis theory is the most general, can be used to describe reactions in non-aqueous solutions. It can even be used to describe reactions between solids. And again, to me, the most important distinction between Arrhenius theory and Bronsted-Lowry and Lewis theory is that for Arrhenius theory, you add it to water. If it produces hydrogens, it's an acid. But for Bronsted-Lowry theory and Lewis theory, it depends on what it's reacting with. In this reaction, what is behaving like? Bronsted-Lowry and Lewis theories are consistent. And so if a compound is behaving like an acid, a Bronsted acid in a reaction, then it's also behaving like a Lewis acid. Now, because Lewis theory is more general, you can have something that's a Lewis acid that is not behaving like a Bronsted acid. Okay, so every time you have a Bronsted acid, you also have a Lewis acid. But a Lewis acid does not necessarily have to be a Bronsted acid because Lewis theory is more general. Now, when we can characterize a compound as being a strong acid or a strong base, we're using Arrhenius theory. And all we're talking about is for a strong acid, you have to water all those molecules break apart or dissociate.
An acid is a substance that produces hydrogen ions when dissolved in water. Hydrogen chloride is an example of a common and important acid. When hydrogen chloride gas dissolves in water, it forms hydrochloric acid. Hydrogen chloride is very soluble in water and is completely dissociated. It is therefore a strong electrolyte. Nitric acid is another common strong acid. Upon dissolving in water, nitric acid completely ionizes to form an acidic solution. Like hydrogen chloride, nitric acid is a strong.
So strong electrolytes completely dissociate into ions when added to water. And so all strong acids and all strong bases are strong electrolytes because when you add them to water, all those molecules break apart into ions. And so on the right, you see nitric acid breaking apart into hydrogen ions and nitrate ions. And so when we think about strong acid, we think about virtually all those molecules breaking apart. Now, if we write down the acid going to hydrogen ions or hydronium ions, that reaction, the Eckhart constant is actually a Ka. And for a strong acid, the Ka is very, very large. And often we'll assume that the Ka is infinite.
Let's view acid dissociation at the molecular level and focus first on strong acids. The concentrated acid in the beaker consists primarily of acid molecules. As soon as they make contact with the water in the flask, proton transfer from HA to H2O occurs for virtually every acid molecule. Note the change from blue to red. Therefore, a strong acid solution consists of hydronium and A- ions in water and virtually no HA. It follows that the acid dissociation constant Ka for a strong acid is very large.
And so again, in strong acids, we assume they completely dissociate. The Ka is very, very large. Often we'll assume that it's infinite. Now, if you notice that we can talk about acids in terms of hydrogen ions, H+. We can also talk about acids in terms of hydronium ions, H3O+. Now, they're actually the same thing. They're actually an approximation for when you have hydrogen ion in water, it's actually surrounded by, on average, I think it's 4 water molecules. But again, please remember, strong acids, we're talking about they just completely dissociate. We're using Arrhenius theory. It's not that they're nasty or they are very reactive with other compounds. It's just that they completely dissociate. And again, H+ and H3O+, the hydrogen ion and hydronium ion, refer to the same thing. They're both just an approximation for having hydrogen ion surrounded by like 4 different water molecules.
A water molecule consists of 2 atoms of hydrogen and 1 of oxygen. Water molecules are attracted to a hydrogen ion, or proton, to form a conglomeration. There are often 6 and sometimes more water molecules around an ion. Because the hydrogen ion is so small, it is thought to have an average of 4 water molecules associated with it at any time.
And so again, instead of writing H+ and then 4 water molecules, we either use H+ or H3O+. They're exactly the same thing. Now, if you look at the reactions on the bottom, you see HCl going to H+ plus Cl minus, and then you also see H2O plus HCl going to hydronium ion plus Cl minus. Those 2 reactions are exactly the same. They're just 2 different ways of writing exactly the same thing. Now remember, pure solids, pure liquids do not appear in the equilibrium expression, and so when you write that equilibrium expression for the bottom reaction, you do not include the water. And hydrogen ions and hydronium ions are the same thing, and so those 2 reactions are exactly the same. So for strong acids, they completely dissociate. Now for weak acids, only a small fraction of those molecules actually dissociate.
Acetic acid is the major ingredient of vinegar. When acetic acid is added to water, it is not completely ionized. It is therefore termed a weak electrolyte or weak acid.
And so strong electrolytes completely dissociate into ions. Weak electrolytes, only a small fraction, actually dissociate into ions. And so all weak acids are weak electrolytes. All strong acids are strong electrolytes. Now on the right, we have the acetic acid going to hydrogen ion plus the CH3COOH minus. Notice that the equilibrium constant's really pretty small because only a very small fraction of those molecules break up into ions. That means it's a weak acid. And so the Ka for weak acids is always very, very small.
Now the beaker contains a weak acid. As before, the moment the acid molecules make contact with the water, proton transfer from HA to H2O occurs. But in a very short time, proton transfer from hydronium ion to A- balances it, and equilibrium is reached. Thus, a weak acid solution has a relatively high concentration of HA and very low concentrations of H3O+ and A-. Therefore, the acid dissociation constant is very small.
And so again, the weak acid, very small molecules that we actually dissociate. And so in a bottle of weak acid, you have mostly the weak acid molecules and a little bit of hydrogen ions and a little bit of the anion. And so on the left, we have HCl, which is a strong acid. Pretty much complete dissociate. Your Ka is very, very large. On the right, we have a weak acid. A very small number of those molecules dissociate, and so your Ka is very, very small. Now notice that HF is actually a really nasty acid. It can dissolve glass. A little bit can actually kill you. And so when we're talking about strong acids and weak acids in this context, all we're doing is talking about ability to what percent of the molecules dissociate when added to water. HF is much nastier than HCl, but again, HF is characterized as a weak acid because only a small fraction of those molecules dissociate in water. And so one question you might see sometime in the very near future is, what is the concentration of HCl molecules, H+ Cl- in a 1 molar solution of HCl at equilibrium? And so first you have to recognize that, well, HCl is a strong acid, so it completely dissociates. So if I have 1 mole of HCl in water, it actually all dissociates. We assume it all dissociates as an approximation. Often we treat Kas for strong acids as pretty much infinite. And so for a 1 molar solution of HCl, it's kind of interesting. We have no HCl molecules. We have 1 molar hydrogen ions and 1 molar chloride ions. And so when we're talking about 1 molar solutions of HCl, we're talking about how it was made. We're not actually talking about the number of HCl molecules in the solution. Now, if we're looking at for a weak acid, HF is a weak acid, what's the concentration of HF molecules, hydrogen ions, and fluoride ions in 1 molar solution of HF? Again, HF is a weak acid, so it only partially dissociates. If we actually want to calculate how much dissociates, we're going to have to do an equilibrium problem. Now, we could plug in 1 minus x, and x into our equilibrium expression and solve it that way using the quadratic equation. Another way of thinking about it is that Ka is very small, 3.5 times 10 minus 4th. And so if Ka is very small, it means x is very small, and x is probably negligible compared to 1. And so we can make this approximation. And now if we plug these into our equilibrium expression, and so we have x squared over 1 equals 3.5 times 10 minus 4th. And so in this case, x is equal to 1.9 times 10 minus 2. And so our approximation was good. X is negligible compared to x. Again, you can do the approximation often for weak acids, and you should always check your approximation afterwards. Now, if we didn't want to do the approximation, we'd plug in these into our equilibrium expression. We'd have to multiply it out, and then we solve it using the quadratic equation. Now, if we do it that way, we get 1.85. Well, here's actually the math of how you do it. So the solution for the quadratic equation is going to be negative b plus or minus square root of b squared minus 4ac divided by 2a. Now notice that for the quadratic equation, you actually get 2 values. You get a plus and minus. And so one value is minus 1.75 times 10 minus 4th, the other is 1.7 times 10 minus 2. Now, always one of the values given by the quadratic equation is going to be wrong. Now, you cannot have a negative concentration, and so it can't be the negative number. It has to be the positive number, and so x is actually 1.85 times 10 minus 2. And so 1.85 times 10 minus 2 from the quadratic equation, and we had, we had 1.9 times 10 minus 2. And so our approximation actually was fairly accurate. The quadratic equation is the correct way of doing it, but the approximation is a little bit faster. And so Kas we use to describe the strength of the acid. And so on the table on the left, they're all weak acids, but the strongest one on the table is HiO3. It's got the largest Ka. Now the weak acid on the table is going to be the HCN. And so again, larger the Ka, the stronger the acid. Now there's 7 common strong acids: nitric, sulfuric, hydrochloric, chloric, perchloric, hydrobromic, and hydroiodic. Now these are all inorganic acids. And so inorganic acids have the hydrogen written in front. Now you should also notice that H2SO4, sulfuric acid, is a strong acid because that first hydrogen comes off easily. Now the second hydrogen, so after you take off one hydrogen from the sulfuric acid, you have HSO4 minus. Now the second hydrogen, removing it from HSO4 minus, becomes more difficult. And so H2SO4 is a strong acid, HSO4 minus is a weak acid. Now I said typically we assume strong acids that come constant. Ka is basically infinite. They are fairly large, they are very large, but they are also very difficult to measure. And here's some Kas of strong acids: 10 to the 11th, 10 to the 10th, 10 to the 9th, 10 to the 7th. But again, typically you'll treat strong acids as completely dissociating, and their constant is basically infinite. Now the name of the acid is actually also related to the name of the ion, the polyatomic ion. And so nitric gives you nitrate, sulfuric gives you sulfate, chloric gives you chlorate, perchloric gives you perchlorate, etc. And so the number of hydrogen ions in the acid is actually equal to the negative charge of the anion. And so nitrate has a -1, and so nitric acid has 1 hydrogen. Sulfate ion has a -2 charge, and sulfuric acid has to have 2 hydrogens. And so often it's helpful to memorize the polyatomic ion and the acid at the same time because they do go together. The name of the acid is related to the name of the ion. As I mentioned before, ic goes with 8. And so I expect my students to be able to recognize these, to be able to memorize the strong acids, and then they should be able to recognize weak acids. And so again, for inorganic acids, you have that H in front. And if you have if you have an inorganic acid and it's not on your list of strong acid, it means it's a weak acid. Now, when you see the COOH group, that means an organic acid. Organic acids, like organic professors, are all weak. And so if you see COOH, think weak acid. Now, polyprotic acids means you have more than one acidic proton. And so H2SO3 is polyprotic, H2CO3, H3PO4. Now, the number of acidic protons does not affect if it's a strong or weak acid. So H2SO4 is a strong acid because that first hydrogen comes off easily. H2SO3 is a weak acid because that first proton does not come off easily. Phosphoric acid has 3 acidic protons, but it's still a weak acid. And so again, the name of the acid is related to the name of the polyatomic ion, and sulfite gives you sulfurous. Notice that suffix is the same. Nitrite gives you nitrous. Carbonate gives you carbonic. Phosphate, phosphoric, etc. Hypochlorite gives you hypochlorous acid. And also you should recognize that there's a system for the naming. And so if you look in the bottom for ClO4-, that gives you perchlorate. If you remove 1 oxygen, it gives you chlorate. Remove another oxygen, chlorite, and then remove another oxygen, gives you hypochlorite. Now it's kind of interesting. You should recognize the naming. You should also recognize that the charge isn't changing. And so the perchlorate ion has 4 oxygen, has a -1 charge. The hypochlorite has 1 oxygen, still has a -1 charge. The oxidation state of the chlorine does change. But the naming depends on the relative number of oxygen, not the absolute number of oxygen. And so sulfate has 1 more oxygen than sulfite. Nitrate has 1 more oxygen than nitrite. Chlorate has 1 more oxygen than chlorite. But notice that the chlorate and nitrate have 3 oxygen, while the sulfate has 4 oxygen. And likewise for the ite, chlorate and nitrite have 2 oxygen, while sulfite has 3 oxygen. And so I expect my students to actually memorize this list of polyatomic ions. As long as you remember the system for the naming, it's not that hard. But again, you see these throughout your chemistry career because they stay together as a group, and they're actually as important as memorizing the elements on the periodic table. And so atoms and polyatomic ion are covalently bound, and so in reactions, the polyatomic ions actually typically stay together. And so nitrous acid, HNO2, converts into hydrogen ions plus nitrite ions. Again, notice that the nitrite is staying together. Calcium hydroxide dissolves in calcium ions and hydroxide ions. And again, hydroxide is a polyatomic ion. It stays together as a group. And so we've talked about strong acids and weak acids. For strong bases, they also completely dissociate when added to water.
Bases are substances that increase the concentration of hydroxide ion in water. Water-soluble ionic hydroxides such as sodium hydroxide, potassium hydroxide, and calcium hydroxide are among the most common bases. When sodium hydroxide is dissolved in water, it completely dissociates into sodium and hydroxide ions. Because sodium hydroxide is completely ionized in solution, it is referred to as a strong base. It is also, of course, a strong electrolyte.
And so for strong bases, their Kb is very, very large. Again, we treat them as infinite. Now for weak bases, they're a little bit different. Again, the Kb would be pretty small, and so you're only producing a small amount of hydroxide group. For weak bases, typically it does not come with hydroxide in the molecule. And so ammonia is our typical weak base, NH3. And what happens is it reacts with water, ripping off a hydrogen ion, leaving with a hydroxyl group.
Ammonia does not contain the hydroxide ion, but is basic in water. When gaseous ammonia dissolves in water, it reacts with water to form the ammonium and hydroxide ions. However, ammonia is a weak base. The equilibrium forming the hydroxide and ammonium ions lies largely to the left. At any given time, most of the ammonia is in a non-ionized form.
And so again, for weak bases, they'll only partially produce hydroxide ions. And so again, most weak bases look like ammonia. The nitrogen has a lone pair, rips off a hydrogen ion from the water, and then you have the hydroxyl group. But ammonia, think again as your typical weak base. It's got that lone pair, and so if we look at electrostatic potential, it looks something like that. And it's that lone pair that's able to remove the hydrogen from the water, leaving you with a hydroxyl group. And so most weak bases have a nitrogen bound to three other things and a lone pair. And so strong bases completely dissociate, like sodium hydroxide. Weak bases, we don't say dissociate, but their Kb is relatively small. You have the base on as a reactant, hydroxide as a product. Now, if you ask the question, what is the concentration of sodium hydroxide molecules, sodium ions, and hydroxide ions in a 1 molar solution of sodium hydroxide, you have to remember that it's a strong base, so it completely dissociates. And so if we add 1 mole of sodium hydroxide to 1 liter of water, all that breaks apart, and you have 1 mole of sodium ions and 1 mole of hydroxide ions. And so again, it's kind of interesting. In a bottle labeled 1 molar sodium hydroxide, you have no sodium hydroxide molecules. You got 1 molar sodium ions and 1 molar hydroxide ions. You have to memorize your weak bases so you can recognize that a bottle of 1 molar sodium hydroxide is 1 molar sodium ions and 1 molar hydroxide ions. Now, if you're asked about concentration of 1 mole of ammonium, what's the concentration of ammonia in 1 molar ammonia, then we have to do an equilibrium problem. So strong bases, strong acids, they completely dissociate. We don't need to do an equilibrium problem. Weak acids, weak bases, we do need to do an equilibrium problem. And so we make the ice table, initial change equilibrium. And so if we start with 1 molar ammonia, and we start with 0 hydroxide, 0 ammonium ion. And so each time X of ammonia dissolved, you get plus X of a hydroxide plus X of the ammonium ion. And equilibrium is going to be the initial plus the change. So 1 minus X, X, and X. Now again, the Eckham constant is very small. In this case, it's 1.8 times 10 minus 5. And so X is probably very small. X is probably negligible compared to 1. And so if we make that approximation, we can plug things into our Eckham expression. So hydroxide is X, ammonium ion is X, ammonia is just 1. And so we solve it and we get X equals 4.2 times 10 minus 3. Now notice in your table, X is equal to the hydroxide ion concentrations at equilibrium. It's also equal to the ammonium ions at equilibrium. And so we've calculated the concentration of all three species at equilibrium, 4.2 times 10 minus 3. Now likewise, with the weak acid, we could also use the quadratic equation. And so again, we have to plug in the expressions. We should solve the quadratic equation. And we get 4.23 times 10 to the minus 3. And so again, very close to what we got for the approximation. But when you do the approximation, always check your approximation at the last step. And so here's a table of KBs. And so they're all weak bases. They all have nitrogen. Their nitrogen always has a lone pair. And so the smallest KB leads to the weakest, and the largest KB leads to the strongest base. And so for strong bases, you're going to have the alkali metal hydroxides, and you're going to have the heavy alkaline earth hydroxides. And again, I should just remind you, strong electrolytes, they dissolve completely, forming ions. Weak electrolytes only partially dissociate. And so all strong acids and strong bases are strong electrolytes. All weak acids and weak bases are weak electrolytes. And so a question you might see in the very near future is what species are present in the following solutions at what concentrations. And so 1 molar lithium hydroxide, you're going to have 1 molar lithium ions and 1 molar hydroxide ions. It's a strong base, completely dissociates. 3 molar HCl, you'll have no HCl molecules. You'll have 3 molar hydrogen ions, 3 molar chloride ions. And so acid-base theories provide a framework for understanding a lot of different compounds, a lot of different reactions. They help us understand some compounds react and why some reactions have larger Ekman constants than others. I hope this was helpful.